Experimental design concepts. Okay, experimental design is how you conduct an experiment. Okay, observational study, data that naturally occurs and is recorded for study and analysis. So observational, you're watching stock market, you're looking at weather data, you're looking at observing temperatures of humans or animals or whatever, things that naturally occur, observational data. A designed experiment, this is a planned procedure to obtain facts or to confirm or deny previous results. And so that is, how did you do this? Okay, so far the only design elements we've talked about are independent samples and dependent samples. How did we do that? I independently assigned these treatment levels or samples, these subjects to treatment levels. Okay, or I have some commonality if they were paired, right? Those are the only two design elements we've talked about so far. Treatment, we've been using it to describe the T different populations, T for treatment. The experimental condition under investigation. Some textbooks will call this a factor, okay, more generically, but we see SSTRT, that's pretty standard for like sum of squares treatment and mean squared treatment. That's pretty standard notation in statistics textbooks. Experimental unit, the subject to which the level of the treatment is applied. So in the case of the wheat example, it's the plot of land. We applied a variety to a small area and measured the yield on it. We apply a medication to a patient. We apply a teaching method to a class, not an individual student, but to a class of students. And then we have the sampling unit or observational unit, the subject on which the treatment effect is actually measured. It may be the experimental unit. So in the case of the wheat example, it was how much wheat came off of a field. And if we're going to evaluate teaching methods, I measure each student. But I've applied the teaching method only once. Right? So the class is the experimental unit. And the sampling unit or the observational unit was the individual student. Those are all, how did you do this? There is always variability in the data we collect. Experimental error is the measure of variation among experimental units treated alike. The most important definition all semester. Experimental error is the measure of variation among experimental units treated alike. So if I have 3 groups and I have those measures, okay, what we're talking about is treated alike, variability this direction. That's what we mean by if they're treated alike, how variable are they? We made the assumption that the populations these came from had the same variance. So I took the variation here, and the variation here, and pooled it together into sum of squares error. Intuitively, if I have more information about a variance estimate, I should be doing a better job estimating it, right? If I increase the sample size. There is also variation among experimental units assigned to different levels of the treatment. And so that when I look at these and I compute, say, a y1 dot bar here, y2 dot bar, y3 dot bar, okay, the variability of those then is this among experimental units, okay, or among treatments. So that is the purple here. Replication. When a treatment level appears more than once in an experiment, it is said to be replicated. So here, whatever this treatment level 1 is, it's been applied 3 different times. Okay, so it's been replicated 3 times. Over here, 5 times, twice. If I don't replicate, I can't measure what? Experimental error. It becomes very important then to us to have more than one experimental unit per treatment level. So in that case of the classroom full of students, if I'm evaluating an instructional method, even though I'm measuring all of the students, I haven't replicated it if I've only taught the method to one class, right? So I have no replication. So that you have to be very cautious then whenever you construct your experiments. Is there true replication, or am I just measuring the same application how many student times, right? If we increase replication, that allows us to measure experimental error. right? Get that variability among things here and improve our precision. So the idea behind our standard error for an individual mean, remember, is mean square error divided by the sample size. Well, if that sample size is larger, the standard error gets smaller. Precision is low variability. When we did all this analysis, we were operating under the assumptions that we had random samples that were independent of each other. Our T populations are normal and our variances are equal. These first two conditions define what we call, in an experimental design, a completely randomized design. So it's just an extension of those two independent samples in the previous class. If you have T independent samples, it's called a completely randomized design, or the acronym CRD is used. So in the wheat example, the 15 1-acre plots, those plots were randomly assigned to a variety, or variety randomly assigned to 5 of the plots. Our experimental unit here was a 1-acre plot. Our treatment was variety. The number of levels of the treatment we had were equal to 3. So we had these 15 plots, if you will, 15 of these guys, and we randomly assigned variety 1 to 5 of those, variety 2 to 5 of them, variety 3 to 5 of them. Okay? That's what made that a CRD. If the design were described in the following way, you have one 15-acre field. Yeah, they're all supposed to be the same size. Okay? And you randomly assign your treatment, so say our variety 2, variety 1, variety 3, variety 1, variety 3. Let me finish the variety 1 so I don't miss them. 3. A variety 1, variety 2. There's some randomization to it. I believe I got 1, 2, 3, 4. Need one more somewhere. And then we had the corner of the field flood is what actually happened, right? This is a CRD. If I had a similar thing, and due to a gradient in the field, varieties are randomly assigned to 1-acre plots within strips. So I come in and I assign a variety 2 and variety 1. This would have to be variety 3 to account for that gradient that moves across the field, right? It's no longer random then. So as soon as I put in the next one, so if I have a variety 1 and variety 2, this has to be variety 3, right? I have to put each one of them in there. So it's no longer random where they're going, is it? This is not a CRD. How did you do this experiment? Well, I randomized part of it, but I didn't completely randomize it, did I? Whenever we looked at the analysis of variance, we wrote out our assumptions as this list. What we typically look at, though, as we move and we start changing how did you do this experiment and the kinds of treatments that you're looking at, we write a statistical model for this. And so that's what we get into then on page 18. We can describe our experiment using a statistical model. A statistical means model, what this means is that we use a mu sub I, just the same notation that we've been doing, identifying the population mean for the treatment level or the group I. And so that we write our data then as our Yij's, just as before, is equal to the mean plus some error. So it's this mean value, this mu I value, and our data actually are somewhere above or below that. These epsilons are these positive values above and below the true population mean. That rather than write out all of this, you'll see statistical models written. Okay, so we have this treatment level I mean, and so this is some fixed but unknowable value. And the concept, as it has been from the start, is that we collect our sample information and we try to estimate what this mu I is, right? If we knew what mu I was that for every population, we would know if they're the same or different or not, right? Okay, but we don't. So we have this fixed but unknowable value. We recognize that we have the errors about these means, and that's where our data comes from. Not every, remember we said there's variability in all the data we collect, so not everything is equal to mu I. Okay, we have an assumption here that our epsilons have a normal distribution about 0, and that we have a variance sigma squared sub epsilon. So what this says is no matter what value of I, no matter what treatment level we're looking at, we have the same variance. So that statement, or that right here, captures items 3 and 4 here. It says all of our populations are normal because of this. That's what that capital N is, and it says all our variances are equal, and they're all equal to sigma squared epsilon. So you don't see this written out as before. We don't have the random samples. Of course, we can always put that on, and independence is also implied here because very often you may see this written as IND, meaning that those are independent of each other. We have some additional notation. I know you might not like the notation, but if I were to walk into your chemistry class, your finance class, or whatever that happens to be, you would expect me to learn to speak the language. So, and you're in my statistics class, you need to learn to speak the language, okay? Whenever you see this notation, this is the expectation of the response, the YIJs, okay? And so this is another way of reading this expectation is the mean of the YIJs. And so that whenever we write the YIJs, I went uppercase here, and I realized on the previous page it was lowercase, so I don't mean anything by that here. I should be consistent, though. So we're looking at the mu i's plus the epsilon sub ij's from the previous model is what the YIJs are equal to. This expectation moves across the sum. We have the expectation of the mu i's plus the expectation of the epsilons. Well, remember, this is some fixed but unknowable value, all right? And so this expectation is the mu ij. There is no randomness to that. And the expectation here, we said that these errors had a mean of 0. That's what that normal 0 sigma squared epsilon meant. Back over here is that this is the mean, and that this is the variance. That notation you should have seen in the previous course, but just in case you've forgotten that. So first one listed is mean, second is variance. Do be careful. I have seen a couple of references where the second one listed will sometimes be standard deviation, but primarily it's variance. Okay, so the expectation of this, then, the average of, or the mean of all these epsilons is 0, so therefore whenever we measure any individual data point, our expectation that it's equal to the population mean. We recognize it's not. There's some error variability. When we look at the variance of all our data, our YIJs, we're looking at the variance of the mu i's plus the variance of the epsilon ij's. Well, again, mu I is some fixed but unknowable value. So if it's a fixed value, it does not vary. If it does not vary, the variance is 0. And the variance of the epsilons is this sigma squared epsilon value. So the y's that we measure have the same variability as the errors. That's why we're using the MSE to estimate that error variance. Okay? What we have then is a number line, let's say, and we have our different values of our means. And suppose we have a mean of mu1, and we're saying that our data are normally distributed about it. Right, so these would be all of our y1j's. Follow this normal distribution. Maybe y2 is a different normal distribution centered at another value over here, the mu2's. All the y2j's then are normally distributed about this, but they have the same variance. The variance here, in each case, sigma 1 squared is equal to sigma epsilon squared. Over here, sigma 2 squared is also equal to sigma epsilon squared. And then we may have a third distribution in here, our mu3, but the idea is that the spread on these distributions is the same everywhere. They're just centered at different places. If the alternative hypothesis is true, if the null hypothesis is true, then they're all right on top of each other, right? So that we can write then for any of our yij's are normally distributed about their mean mu I, and they have the same variance sigma squared epsilon. So that's what's called means model notation. If you're going to be looking at other references in addition to ours, you also need to be aware that there's also what's called a statistical effects model. In the statistical effects model, we have mu plus tau i's plus the epsilon ij's. Okay, our indexing is the same, but notice now our mu is no longer indexed, and we have this tau I effect. And so that we have this mu is the value of an overall mean, which again is a fixed but unknowable value. The tau i's are also these fixed but unknowable values. And then we have this random error due to which observation it is in the particular treatment group. We have the same error variance assumption. So doing the same thing as we did with the previous one, our expectation here then is the expectation of this effects model, mu plus tau I plus the epsilon ij's. And then the expectation, we move across each term, expectation of mu, the expectation of tau I, plus the expectation of the epsilon ij's. All right, again, this fixed but unknowable value, its expectation is mu. Likewise, the expectation of the tau i's is tau I, and the expectation of our errors is 0. So we expect then each of our observations to be, the mean of all those, to be this overall mean mu and these value for tau I. So the I is the same as the I index here. So if we have y1j, we would expect its expectation is mu plus tau 1. And again, with the variances, we can do a similar thing that here, whenever we look at our individual data values, the yij's, the variance of the mu's, plus the variance of the tau i's, plus the variance of the epsilon ij's. Right? If these are fixed but fixed values, then mu and tau I do not vary, so they contribute 0 to the variance of our data. And the only variability we have is that due to the epsilons, which again is sigma squared sub epsilon. And so that, I won't draw out all of them, but the idea then here is that we have these normal distributions, and the center of this is given by our mu plus tau I. Each will have t different distributions like this, each centered at their respective mu plus tau i's, and they all have the same variability, sigma squared epsilon, right? So in our means model notation is what we've been using to write our null hypothesis for analysis of variance. That is, we have the simultaneous equality of these t treatment level means, or these t population means. If we wrote this in effects model notation, we would have mu plus tau 1 is equal to mu plus tau 2, etc., all the way to mu plus tau t. Well, the mu's are the same everywhere, so that would be equivalent to seeing the simultaneous equality of the tau i's, right? So again, depending upon the references you read, you may see it written in this form, or you may see it written in effects model notation. So I point this out so that, again, it's like if you're doing some alternate reading for this course, I don't want you to be tripped up by the models there.